Hi everyone, this is Kelsey, and today we're going to talk about Laplace's equation in cylindrical coordinates. So to do that, we need to talk about the problem that we're trying to solve and how cylindrical coordinates work in general. So the problem we're trying to solve is we have a cylinder over here with with a height of h, a radius of a, and the bottom and the outside curved edge, it's all grounded, so it has a potential of 0. The top has a potential of negative V1. Now I've put this cylinder on a coordinate system with the origin at the bottom here, and the way this works is if we have a point out here on the cylinder or just on the coordinate system in general, the length from the origin out along the xy plane towards that point is s, and then the angle from the x-axis towards the y-axis towards that point is phi, and the height of that point along the z-axis here is z. Now we need to consider the problem as previously discussed, and consider some boundary conditions that we have. The first is that at z equals 0, v equals 0, so that just means that the bottom of the cylinder is grounded and the potential is 0. At z equals h, v equals negative v1, so at the top of the cylinder we have a potential of negative v sub 1. And at s equals a, v equals 0, so that means the rounded portion, the outsides or the sides of the cylinder are also grounded and the potential is 0. And then it's also important that when phi equals 0 and phi equals 2 pi, which would be the x-axis here, that it's the same, the potential is the same value from the equation. So that just means that we want it to be continuous at the x-axis, or continuous in general, and that it's periodic. Okay, so here's the form of Laplace's equation in cylindrical coordinates. Del squared v equals 0. And then we have del squared v equals 1 over s d ds times s dv ds plus 1 over s squared d squared v d phi squared plus d squared v dz squared equals 0. We're going to assume that we can solve this equation using the separation of variables technique, in which the potential equation is going to equal the product of 3 separate functions or equations, all of which are each only depend on one of the variables. So we're going to start by taking our del squared v to our Laplace's equation, which is equal to 0, and taking our form up here, plugging it in down here, and multiplying it by this separation of variables equation. So we end up with something like 1 over s d ds times s dr, which comes from here, over ds times phi and z, plus s squared plus 1 over s squared d squared phi from here, over d phi squared times r times z here, plus d squared z, which comes from up here, over dz squared times phi times r, there, equals 0. Then we're going to take and divide by the equation, so r phi z, and ultimately we get what is down here, which is 1 over s d ds times s over r dr ds plus s squared 1 over phi d squared phi over d phi plus d squared z dz 1 over z times 1 over z equals 0. Our next goal is to take one of these terms and make it a constant. So as you can see here, we're going to do that with the z term, or what I've called the z function. So we need to revisit the boundary conditions in order to have an idea of if this constant should be positive or negative that we're going to make it. So boundary conditions are that that this function needs to be 0 in one place at z equals 0. So this is at the bottom, but it needs to be non-zero up here at the top. Therefore, we want hyperbolic sine and cosine functions because they do this. They go to 0, but they also then can be non-zero. And because we want hyperbolic sine and cosine functions, we want a constant that is positive, or we're going to have a constant that's positive. So we're going to call this constant k sub n, or specifically, we're going to set this equal to k sub n squared. So this is just this here. And then we're going to rearrange it a bit so that we have d squared z over dz equals k sub n squared of z. Okay, the next thing we're going to do is we're going to take the z function and we're going to plug in our hyperbolic cosine and sine like this. So we have a hyperbolic cosine k sub n z plus b hyperbolic sine k sub n times z. And we're going to look again at our boundary conditions. So this time z equals 0, b needs to equal 0. So the z is 0 needs to equal 0. So if we plug 0 into the equation, we have a hyperbolic cosine times k sub n times 0 plus b hyperbolic sine times hyperbolic sine of k sub n times 0. That all needs to equal 0. Now the sine of 0, or the hyperbolic cosine of 0, always equals 0, so that's gone. So then we have a of hyperbolic cosine k sub n times 0. That needs to equal 0. In order for that to happen, a here, this constant, needs to equal 0. So if that constant always equals 0, then what we have left for the z function, the z of z, is b hyperbolic sine of k sub n times z. The next thing we're going to do is look at the phi function. So we've taken this equation up here. We've put this in for this, and we're left with this. Okay, then we're going to multiply the whole thing by s squared. This is going to get rid of the s squared term here, which is currently causing a problem because we want each of these terms to only depend on one variable, and we have s's and phi's here, which is a problem. So if we multiply everything by s squared, we end up with only s's over here still. The s's are gone over here, so we just have phi, and then we have s squared k sub n squared here, and it all equals 0 still. Now we're going to try to make this piece a constant. We're going to follow the same procedure as before. We're going to look at boundary conditions, and then we will go from there. So the boundary conditions here is that the potential, or v, must be the same value at 0 and 2 pi, which means we're going to want sine and cosine functions because they are oscillate and periodic, so they'll return to the same value over a period of time. And because of this, we need a negative constant. So this time we're going to call our 1 over phi d squared phi over d phi is going to equal negative m squared. Then we're going to look at our cosines and sines. So we have our phi, and we have c cosine m phi plus d sine m phi. So because of symmetry and our boundary conditions, m has to equal 0. So if we plug 0 in here, we get c cosine of 0 plus d sine of 0. And ultimately, because the cosine of 0 is 1, the sine of 0 is 0. We ultimately get that this equation equals C. And so we have that phi equals C. Okay, now remember we are going to combine our equations together to get an ultimately get an equation for the potential here. So that was going to be the R sub S times phi, or not R sub S, but R of S, phi of phi, and Z of Z. So remember that we've just determined that Z of Z is B hyperbolic sine K sub n times Z, and that phi of phi equals C. So ultimately, so far we have the V of S, phi, and Z equals R of S, which we haven't solved yet, times C times B hyperbolic sine K sub n Z.
All right, so just moving on from where Kelsey left off, I just wanted to make a few clarifications here. So when we're looking at our differential equation for the phi component of V, as Kelsey said, due to symmetry, we know that m must equal 0 here, because otherwise these will just be oscillating at different rates. So this, when m equals 0, becomes 0, and this becomes 1. So we know that if m equals 0, then a sub 0 must also equal 1 here, which is important because there's no phi dependence here. As you're moving in a circle, changing their position around the cylinder, v should not change. And so these should be the answers that we got from Kelsey for our z component and our phi component. And so if we're looking at the Laplacian again, grouping it into the same terms, we can substitute the answers we got here for the phi double prime and z double prime here to make it a little bit easier on ourselves. And so this z phi double prime becomes z times negative m squared phi from here, and this phi times z double prime becomes k squared z phi from up here. And then this all simplifies down. We can factor out these phi z's here. So this phi and this z, this phi and this z become 1. And we're left with the Laplacian equals r double prime plus 1 over r prime, plus negative m squared over r squared r plus k squared r. And just to clean up the coefficients a little bit, we can multiply everything by r squared. And then we get 0 equals r squared r double prime plus r times r prime plus the quantity negative m squared plus k squared r squared times r. And so making the substitution x equals kr here, we can make this equation into this form: 0 equals x squared times d squared r over dx squared plus x times dr over dx plus x squared minus m squared r. And this is of the form known as Bessel function, or Bessel equation. And so Bessel's equation, j sub m of x, there's like some graphs. It is a sort of like dampened oscillating function, where little j sub n here that I've labeled in the graph are the nth roots of j sub 0 specifically, because we know that m equals 0 from the no phi dependence here. So we know that we are working with j sub 0 of x. And so this lets us do a few cool things here, but this tells us that big R sub r is equal to j sub 0 of x, which is equal to this function, which I think I pulled from J.D. Jackson, Classical Electrodynamics. It's not super important to use this because we can just say it's this, but just for information's sake. And we can plug in our last boundary condition here, where we know that at the rectangular face of the cylinder, the potential must also equal 0. And so using the x equals kr substitution here, we know that big R when little r equals a, which is the radius of the cylinder, should equal 0. So then r of r equals a is equal to j sub 0 of x equals ka, since r equals a in this sense, or in this case, which is equal to j sub 0 of j sub n, since these are the nth roots of j sub 0, which tells us that ka equals j sub n. And since a is a constant, we know that k must also depend on n. So then k sub n equals j sub n over a. And so plugging this back into our ansatz, we have, since we need to be summing over the index n, the sum from n equals 1 to infinity of j sub 0 times j sub n times r over a, since k sub n equals j n over a, times 1, which is the phi component here, times negative a sub n sinh k sub n z, which is the z component here. And then we have actually one more boundary condition, I lied. So we know that at z equals h, the potential is equal to negative v1, since we're holding it at a constant voltage there. And so we have v1 equals this expression here. And so I didn't know how to solve this. It takes some Bessel function identities that I wasn't aware of, so I did some reading. I found a example from Richard Fitzpatrick from University of Texas at Austin, who came up with this expression here for a sub n. And so this makes this our final potential expression with this a sub n here. And then for the electric field, we know that the electric field is equal to the negative gradient of the potential, which is written out looks like this. We know that because there's no phi dependence, this is equal to 0. So we're just looking for the r component and the z component. So partial v partial r is equal to this sum, and this doesn't depend on r, so this just stays the same. And then we can take the partial with respect to r of j sub 0 k sub n r, and this actually happens to just bump the index up 1. So it becomes j sub 1, which you can see in this graph here. And then this makes partial v partial r equal to this sum here. And then partial v partial z, since this is the only thing that depends on z, this is the thing that we can take the derivative of with respect to z. We know that this is just cosh, and then chain rule brings this out front. So then we can rewrite the full expression for the electric field here with the r hat component and the z hat component here. And then with regards to the charge density, I ran into a few issues because I realized that because we don't know anything about the electric field outside, it's kind of hard to use Gauss's law in this case. So without more information, I think it's maybe impossible to find the charge density on the shell. I could be wrong, but what I ended up doing was just gluing another identical cylinder on top of our existing one to make the electric field symmetrical across the top face. And what ends up happening is if we apply Gauss's law here, then we get that the enclosed charge over epsilon naught is equal to 2 times the integral over the top of the puck here, times, or the integral over the top of E vector dot dA vector plus the integral over the bottom here, which is the integral from negative epsilon down here to positive epsilon up here, and of the integral from 0 to 2 pi of E vector dot r hat, which is just the E component, or the r component of E, d phi dz. And we know that since there's no phi dependence here, this just becomes 2 pi pulled out front. And interestingly enough, the integral from negative epsilon to epsilon of the r component dz, since the z component of E, or the r component of E here, the only thing that depends on z is sinh, we know that it's just cosh, and cosh from negative epsilon to positive epsilon across this boundary would just be equal to 0 since it's symmetric. So this whole expression becomes 0, and then we're just left with this part here. And that would be equal to this expression here. So we have Q enclosed over epsilon naught is equal to 2 times 2 pi, since, again, the phi component just goes to 2 pi here, or times the integral from 0 to a of the z component of E times RdR. But also, interesting to note here is that the enclosed charge should be equal to 2 pi times the integral from 0 to a of the charge density in terms of A times RdR. And since we have two things that look pretty identical, we can show that since we have this integral from 0 to a of a something times RdR, and then this integral from 0 to a of something times RdR, then we can just set these equal to each other. And then we get that 2 pi times the surface charge density is equal to 4 pi times epsilon naught times the E component of Z. So in this case that I've created, this would be the charge density. Otherwise, we don't have enough information, I don't think.